I'm Michael, and today I'll be talking about training autoregressive dynamics models. We specifically focus on training them for offline policy evaluation and optimization. This is joint work done with collaborators from Google and DeepMind. Model-based RL has been shown to achieve impressive performance on real-world tasks and improve the sample efficiency on a variety of different control tasks. In this work, our goal is to further improve these dynamics and reward models by making predictions in an autoregressive way. However, evaluating models can be tricky. As you can see in the slide given from a tutorial on model-based RL last year, a typical model is used in many different places, from simulating the environment to strengthening the policy itself. To help combat this objective mismatch and better evaluate our models, we choose instead to focus on the fixed dataset setting. In this setting, we're given a static data set of state, action, reward, next state tuples, and our goal is to train a conditional generative model which predicts the next state and reward given the current state and action. This is also known as offline setting, and it is of real-world interest because there exists many domains where you have a fixed data set, but it can be expensive or dangerous to collect additional data, such as in robotics or healthcare. So the standard approach for training these feed-forward models is to take in the current state and action, feed it through a few fully connected layers, and then output a multivariate Gaussian, which parameterizes the next state and reward. So we predict the mean and the standard deviation for each state dimension. In this setup, each of the state dimensions is conditionally independent of each other given the input. To make a change to the existing architecture and make it autoregressive, we instead predict each of the state dimensions one dimension at a time. And for each new state dimension, we augment the input with the previously predicted state dimensions and a one-hot encoding telling the network which state dimension to predict next. So we opted for a rather simple change to the existing architecture to not confound potential improvements to differences in the architecture. We evaluate our approach on the DeepMind control suite, specifically on a recently proposed benchmark for deep off-policy evaluation, which consists of 9 different control tasks and policies trained on each of these tasks, which are trained on tasks that range from carpal, which is 40,000 data points, to humanoid tasks, which is 67 state dimensions and 3 million transitions. We evaluate our performance by training on 80% of the data and reporting the held out log likelihood on the remaining 20% of the data. So in this case, since we report negative log likelihood, lower numbers are better. And you can see that the autoregressive model achieves a lower negative log likelihood across all 9 tasks in our hyperparameter sweep. We also report the average performance of the 5 best performing models on the sweep, when we also do better there. You can also see that these improvements hold across different architecture sizes. So in these plots, each point corresponds to a single model, and we report the number of parameters on the x-axis and the negative log likelihood on the y-axis. So you can see that as we vary the number of parameters in the architecture, the autoregressive model shown in red still achieves a lower negative log likelihood than the feed-forward models, which are shown in blue. Once we have our models, we can use them for off-policy evaluation. We simply take our best performing model and then it plays the role of the environment when evaluating policies on that task. So we sample our initial state and then we sample actions from the policy that we want to evaluate, and we sample the next state and a reward from our dynamics model. We repeat this to generate a trajectory, and then we can sum up the 2 rewards to get a discounted or undiscounted return. So in contrast to other OPE algorithms, such as fitted queue iteration, we only need to train a single model to evaluate all the policies we want on a given environment, whereas other approaches potentially need to train another queue function approximator for each individual policy. You can see the performance on a few of these tasks here. So each point here corresponds to a different policy. We show the ground truth returns on the x-axis, and then we show the returns estimated by each OPE algorithm on the y-axis. You can just see that the autoregressive model, again in red, has OPE estimates that better correspond to the ground truth estimates. And we can see the correlation numbers here in the title of each plot. We can summarize our results across the 9 different tasks by computing summary metrics, such as the absolute error, where lower is better, and we achieve the lowest absolute error, and also the Spearman rank correlation across the 9 tasks. So this is the median Spearman rank correlation. Finally, we can also use these models for policy optimization. Here, we use them for data augmentation and for model-based planning. You can see that the autoregressive model achieves as good or better performance across the different tasks we tried. And in the case of cheetah run and fish swim, we actually beat the previous state of the art. So overall, we believe autoregressive models are an exciting direction for future research in model-based RL. Thank you for listening.